Today we're going to have a look at titration calculations. During a titration, we have two chemicals, one in a burette, one usually in a conical flask, and we add them together and we reach an end point, and the end point is the point where the chemicals have exactly reacted together. So in the example I've got here, the sodium hydroxide and the hydrochloric acid would have exactly neutralised at the end point. Usually we would add an indicator for an acid-base titration because that gives us a colour change which tells us when we've got there, and we record the value of on the burette that we've used in the table as the titer. So you can see initial and final. Initial is where it started, final is where it finished, and then titer is the difference. It's worth being aware that it doesn't have to be an acid and a base. It could actually be any two chemicals that react together that we can use either a colour change that actually happens in the reaction, so that would be self-indicating, or we can get an indicator for, or some other way of indicating that the reaction has completed. So it doesn't have to be an acid or a base, but most things that you come up across in Year 12 will be acid-base. So how do we process these results? Well, the first thing I want you to notice is that this first column here is the rough column, and the rough column is where we put the results that we take first. And what we do is we start, it doesn't have to be at 0, but usually people would start at 0 for the rough one, and then we empty out relatively quickly until we see a colour change, stop and record a rough idea of how much has gone through. It's not particularly precise, it's quick, and the reason that we do it is so that when we come on to the second, third, fourth, etc. Titrations, we can empty pretty much this amount minus about a centimetre cubed. So in this case I would empty maybe 11 centimetres cubed out straight away by completely opening the tap, and then I would add the last few drops drop by drop really slowly so that we can get a nice accurate result. Now because of this, we're not going to include the rough titration in our final average. What we're looking for is we're looking for two results that are concordant, and concordant means within 0.1 centimetres cubed of each other. Now it's true that my first titration here is concordant with my rough one, but because I know that I rushed the rough one, because I know I let everything out really quickly, it's not correct to use that rough one. That was not a precise measurement. That was done in a hurry as a convenience rather than as an accurate result. So even though this first one is concordant with that one, we're not going to use the rough one. We're going to continue doing our titration until we get concordant results. You can see that my second one here, it's gone a little bit over. There's too much added. These are 0.6 apart. They're not concordant. This one is concordant, and so therefore we're going to use these two results. Now at this point we can stop the titration. We don't have to fill up this last column, we don't have to do another experiment because we have concordant values. So what we do with the concordant values is we calculate an average titer, and that would be in this case 12.10 plus 12.15 over 2. And at this point, on mark schemes in the most recent papers, it's asked for, well, it hasn't asked for significant figures or decimal places, but the mark scheme has usually given the answer as 2 decimal places. Although there's not really because there's no guidance, it's perfectly fine to round it to 3 significant figures. I would tend to round to 3 significant figures here. So we would end up with 12.1 centimetres cubed as our average titer. It would actually be 12.125 on a calculator, but I'm going to round it to 3 significant figures. I think that's likely to be acceptable for the mark scheme because it doesn't specify any number of decimal places, but read the question to make sure. So once we have our average titer, we get to the crux of the matter. What is a titration for? Well, a titration can be used to work out something about an unknown solution by reacting it with a solution that we know more about. So, for example, if we know the concentration and volume of our hydrochloric acid in the first example, then we would be able to work out the concentration of the sodium hydroxide if we got a volume. Now in this example, obviously you can see that I know the concentration and the volume of the sodium hydroxide, which means that if I know the volume of the hydrochloric acid used, we can work out the concentration of the hydrochloric acid. So it doesn't matter which way round it is, it doesn't matter what the two chemicals are, we always have one of which we know the concentration, and we have a volume in our conical flask, and we have a volume in our burette. And so, depending on which one it is, we will have to change our method slightly, but the method is always following the same logic, and the logic is this. We start by using, for an acid-based calculation anyway, we're going to start with concentration equals number of moles over the volume, and the volume in this case would be measured in decimeters cubed. I've got 0.2 capital M standing for moles per decimeter cubed here, so if it's moles per decimeter cubed, our volume must be in decimeters cubed. Now we can put that into the formula however which way we like, and I'll show you that in a minute. But what that means is that N, number of moles, is equal to C times V. And all we're going to do here is we're going to use these two rearrangements of the same equation. So, the first thing that we want to do is we want to work out the number of moles of the known substance. Now, if we look at my example here, the known substance is the sodium hydroxide because we have 25 centimeters cubed of it and we know the concentration. Read the exam question, and the volume in the flask will be in the question somewhere. So, N, I'm just going to put NB for the base. Okay, so N of the base is equal to, so C times V would be 0.2 multiplied by 25 centimeters cubed, which we're going to divide by 1,000 to put it into decimeters cubed. And if we put that through our calculator, we end up with 5 times 10 to the minus 3 moles. So knowing the number of moles of the base now, we have to construct an equation. If we know that the NaOH and the HCl react in a 1-to-1 ratio to make NaCl and H2O, then the number of moles of the base must equal the number of moles of the acid. So number of moles of base equals number of moles of acid. I'm just going to put A for acid. If your equation was different, if you had like something like sulfuric acid, and you had 2 moles of sodium hydroxide going to 1 mole of sulfuric acid, you'd have a 2-to-1 ratio. And then you'd have 2 moles of base for every 1 mole of acid, and you'd need to do a conversion there with normal stoichiometry. But in our example, we have a 1-to-1 ratio. So the next step is, if we know that the number of moles of the base equals the number of moles of acid for us, we have 5 times 10 to the minus 3 moles of acid as well. And because we know the number of moles of acid, and our acid was in our burette, the burette has an average titer of 12.1 centimeters cubed used. That is the volume of acid, so the number of moles is 5 times 10 to the minus 3 divided by the volume, and the volume here is 12.1 divided by 1,000, and there are various different ways of writing that. You could write it as, you could do that sum first. You could put 0.0121 down here. Mathematically, that's the same as what you'll see in quite a lot of the time in mark schemes, as being 12.5 and then put times 1,000 over the top. And mathematically, that's the same as taking 12.5, dividing it by 1,000, and then putting it into the fraction. Either way, however you do it, you're going to end up with 0.4 moles per decimetre cubed. And that is the concentration of our unknown substance, in this case the acid, and that's basically the same procedure for every single titration that you're going to come across. Take the number of moles of the substance that you know the concentration of volume of, work out the number of moles for that, use a molar ratio to work out the number of moles of the other thing, and then use that number of moles divided by the other volume, the volume of that substance in the experiment, to work out the concentration.